The space-time interval, starting from the principle of the constancy of the speed of light, grounded in the Michelson-Morley experiment, together with the principle of special relativity, we derived the Lorentz transformation. Through the relativistic velocity addition rule, we then confirmed that no object can exceed the speed of light. However, underlying these facts lies a deeper geometric structure. Let us explore this structure through the propagation of light. As we shall see, this exploration will lead us naturally to the concept of the space-time interval, a quantity that remains invariant across all inertial frames. In frame S, suppose a flash of light is emitted from the origin at t equals 0. The light expands as a spherical wave. At time t, the wavefront is a sphere of radius ct, x squared plus y squared plus z squared equals c squared t squared. This describes all points reached by light at time t. Now consider the same light flash as observed from frame S prime, moving at velocity v relative to s. By the principle of the constancy of the speed of light, the light must also expand as a sphere in S prime. X prime squared plus y prime squared plus z prime squared equals c squared t prime squared. Same form, different coordinates. According to the principle that the speed of light is invariant in all inertial frames, these two equations must remain invariant under the Lorentz transformation. Let us verify this. The S prime frame equation can be written as. Now substitute the Lorentz transformation. This section involves calculation, so please pause the video and work through it at your own pace. The S prime frame equation under the Lorentz transformation gave us the S frame equation. Now let us reverse this. Apply the inverse Lorentz transformation to the S frame equation. This section involves some calculation. Feel free to pause the video and work through it at your own pace. We have applied the Lorentz transformation to both the S and S prime frame equations and found that the light sphere equation is identical in both frames. This means that this expression is an invariant quantity in all inertial frames. This expression has units of distance squared. Since this quantity is equal in both frames, it represents a distance that is invariant across all inertial frames. We define this invariant as the space-time interval. For two events infinitesimally close in space-time, Event 1, ct, xy, z. Event 2, ct plus c dt, x plus dx, y plus dy, z plus dz. The infinitesimal spacetime interval, line element, is ds squared equals minus c squared dt squared plus dx squared plus dy squared plus dz squared. This quantity is invariant under Lorentz transformations. Minkowski spacetime. We will introduce Minkowski spacetime, the spacetime structure of special relativity. Since the line element ds squared is deeply connected to this concept, let's first examine its physical meaning. We begin with ds squared for light's path. The line element for light is 0 in all inertial frames. From this condition, let's derive the speed of light c in each inertial frame. For light's path, ds squared equals 0. Applying this condition in different inertial frames, we find that the speed of light is c in every frame. Even when the direction changes, the speed remains c. In other words, the condition ds squared equals 0 expresses the principle of the constancy of the speed of light. Let's illustrate light's trajectory in Minkowski spacetime. For simplicity, we show only the positive directions in the CTX diagram. From ds squared equals minus c squared t squared plus x squared equals 0, we get c squared t squared equals x squared, or ct equals x. This is light's trajectory, which forms a 45-degree line in all inertial frames. Since nothing in this universe can exceed the speed of light, only light's trajectory and the region inside it are physically allowed. Mathematically, this corresponds to ct equals ax, where the coefficient a is 1 or greater. Example, for ct equals 2x, we have x over t equals 1/2 c, representing motion at half the speed of light. We extend the Minkowski spacetime diagram. Light travels along ct equals x and ct equals minus x. The origin O, ct equals 0, x equals 0 is the present moment. Ct less than 0 is the past. Ct greater than 0 is the future. These light trajectories have ds squared equals 0 and are called light-like or null. The region where ds squared less than 0 is called time-like. The region where ds squared greater than 0 is called space-like. ds squared less than 0, time-like region. The time-like region has ds squared less than 0, meaning this is our world where nothing exceeds light speed. Causality is preserved in this region. That is, past, present, and future are connected, and the order of cause and effect is maintained. Past event B and present O, future event A and present O are causally linked and can be connected by world lines. Space-like region. In the space-like region, ds squared greater than 0, which means the space-like region has ds squared greater than 0, representing the region beyond light speed. Since we cannot exceed the speed of light, we can never reach this region outside the light cone. We cannot have any causal relationship with events in this region. From the fact that the speed of light is constant for all observers, we derived a new invariant quantity, the spacetime interval ds squared. This gives us a solid and frame-independent physical quantity. The interval ds squared takes 3 distinct forms: ds squared equals 0, ds squared less than 0, and ds squared greater than 0. The boundary defined by ds squared equals 0, the null interval, separates the regions that are physically accessible to us from those that are not. While we have represented Minkowski spacetime as a CTX plane for clarity, its true structure is cone-shaped, known as the light cone. Since the speed of light is the ultimate speed limit in our universe, causality is preserved, and past, present, and future are not merely distinct, but bound together in an unbroken chain of cause and effect.